When we expressed Gauss's law, we were looking at cases in which we had point-like charges. But in fact, we may have something which is a little more complicated. So let's look at a situation like this. Here's a closed surface. This is not our physical charges. Inside that closed surface, we have a source. And I'm going to think of my source as a bunch of little volume elements in our source. And the amount of charge that I want to calculate that's enclosed in my enclosed surface, in my surface S, well, I have to figure out how much charge is inside this source. And the way we look at that is we say that dq is equal to the charge density, rho. So this is charge density. It's a volume charge density. And we multiply that by the volume element, dV. And so when we talk about the charge that's enclosed, and I'm going to give it a color here, in this enclosed in the Gaussian surface, here's our source. This is the charge enclosed, then is just the integral over the source of the density times the volume element. And our Gauss's law now looks quite complicated. It's a surface integral over a closed surface S. By the way, this closed surface we call the Gaussian surface. And that's equal to 1 over epsilon naught times another volume integral over the source that's enclosed in the Gaussian surface, and that's rho dV. Now, this is the formal description of Gauss's law. It looks quite difficult because we have surface integrals and volume integrals. But what you'll see is that in our physics class, we will just look at special cases where there's enough symmetry that makes both of these sides of this equation reasonably straightforward to calculate. I say reasonably, but it is still difficult. And what we'd like to do now is just give you an overview of those special cases.